Hi everybody, welcome back to the channel. And I made a new video now after the video I just made was network analysis. That is part of the electrical fundamentals series. There is also one about basics of circuits and electricity and stuff. That is very super basic. That's like things you might have learned in school. Now, this one is going to be circuit components, including capacitors and inductors, and we're going to dive deep into them. We're going to look at transient circuits, a circuit that charges or discharges capacitors. And yes, let's start. So, these are the things that we are going to be covering today. We have three building blocks: resistors, capacitors, and inductors. Okay, and so these are the components that we are going to talk about. We'll have RC transient circuit and RL transient circuits. Okay, so these are the symbols of resistors, capacitors, and inductors. Okay, as you see here. We have seen the resistor before, obviously, because in the previous videos we talked about resistors a lot. And then we also have now resistor. The symbol for a resistor is a rectangle. Okay, but before we used to use like it's a very old like symbol. Some people still use it. Is zigzags. Okay, as you see here. Okay, so this is something very interesting. We have ideal versus practical components. And when you have a component, for example, in real life, a resistor is not just made up of an actual resistor. It could be a resistor, a capacitor, and two inductors, but the values of each one is different. Okay, so that makes the resistor to be the component that resists for a circuit. And then you to make that kind of the job for that the resistor. Okay, that but then you can have a capacitor kind of with the same elements but in a different way. You know what I mean? For example, a wire wound resistor is a coil of resistive wires that also has, as you see here, the practical resistor. I put a circuit there that also has two inductors and a capacitor in parallel, right? But when we are learning it in theory for now, we are going to take it as an ideal component. So when we want to talk about resistor, we just say a resistor. We want to talk about capacitor, we just say a capacitor. Okay, right. So first of all, a capacitor. What it does, it actually just stores electrical charge on two metals separated by an insulating dielectric. This dielectric could be air, it could be paper, it could be plastic, and there's even a material called mica, which is I don't know, do they say mica or mica? I don't know, but I've heard about it a lot, and I bet you did as well. So you might ask yourself, well, doesn't that what the battery does? No. This one, it stores the electrical charges. It doesn't let it flow, it stores it, and we use it when we need. It makes it flow, but it don't have voltage. It's just charge. Okay? So now we see on the right hand side, we've got a drawing of two metal plates, and then we got a wire going through it. Okay, plate 1 is a positive charge and plate 2 is a negative charge, and then in between them is our insulating, we call it an insulating material, we call it the dielectric. Okay, now to find the capacitance, okay, of a capacitor, so just like we say resistor, we say the resistance of a resistor. Here we say the capacitance of a capacitor. We use this formula. So permittivity of free space, that's just a constant. You will always have it. And then you multiply it by relative permittivity of the dielectric. So that depends. If your dielectric is air, it's always going to be 1, but if it's some other material, then it will have a different number, which is usually given in questions, tables, data sheets. And then you have the area, so that is the plate area, okay? One plate, what's the area of it? Then you got D, the plate separation, so from one plate 1 to plate 2, what the distance is. So as you see, the formula, that is epsilon, I think. Yeah, another Greek letter. There we go. Epsilon 0 times epsilon r multiplied by A over D. Right, and what is the units? The units is farads, okay, and definitely it's gonna be named after the person who found out about it, because that's always the case. So yeah, usually we actually put the units in millifarads or nano or micro because capacitance is very small. If you have a large amount of capacitance in a capacitor, that is actually very dangerous. Usually we'll have it in terms of like in decimals times 10 to the minus 3 or even less. Yeah, let's go next. Right, charge, energy, and current. We have talked about charge and energy and current in our first video about the series, basics of and concepts of basic concepts of electricity. So yes, always you have these formulas. You will have to either remember them or they're always given in your exam. But I don't think there's point of remembering stuff. All you have to do is understand it. So here you have charge equals the capacitance times the voltage that goes through the capacitor. And if you want to find the energy stored in the capacitor, because a capacitor stores charges, so therefore it stores energy, which is going to be half of the capacitance multiplied by the capacitance through the voltage through the capacitor squared, okay? And then we can find the charge using integration actually. And that is because remember how we find Q using current and T, right? Because charge is a function, right, of current function of time. So you could integrate the function of time of current. Yeah, and IT so equals C times the change in voltage in the capacitor over time. Okay, now we've got an example on the right. You could pause it, you could watch it. I really don't like making my videos long because I want you guys to like understand stuff in the shortest amount of time, but I appreciate the fact that I actually cover a lot of concepts in just one video, and that's the reason it's very long. Right, now here is the symbols and common types of capacitors we have. So the type of capacitor is different to another by the dielectric that is used. So here we have on the left side the standard capacitor, and on the right side we have polarized capacitor. Polarized capacitor could be positive or negative, okay? Now, first is paper, or what we can say metallized paper. So it's foils interleaved with waxed paper, okay? So these are weird materials, I know. And metallized version is self-healing after breakdown. This is more of material science. So if you want to dig deeper into it, you could pause the video, read it, and if you find it very cool, then yeah, you could search into it more. Okay, so capacitors in parallel. How do we add them up? It's opposite to resistors. You actually add the capacitance of each capacitor together. Okay, here is an example. If you have C1 that is 2 microfarads and then 5 microfarads, 9 microfarads in parallel, you just add them up. You get 16 microfarads. Right. And then in series, again, opposite to the resistor, you add them just how you add resistors in parallel. That is 1 over total capacitance equals 1 over C1 plus 1 over C2 plus 1 over how much ever capacitors you have in series. Okay, so right. We have 2 capacitors in series, okay? So we know that the voltage supply is 200 volts, and each capacitor is 6 microfarads, the other one 10 microfarads. Well, what happens in a series capacitors, they share the voltage, right? But more like most thing that we have to remember is that the charge will be shared equally to each capacitor. So if we want to find how much voltage is given to each capacitor V1 and V2, we will have to know that Q equals CV. Q is the charge. So 6 V1 should equal to 10 V2. And also, because of Kirchhoff's, we know V1 plus V2 equals 200. Okay, so now we use a substitution, so simple maths. We can conclude to V1 equal to 125 volts and V2 equals 75 volts. Now, that way we know what we can use either 6V1 or 10V2, okay, to find the total charge, because we said the charge in each capacitor should be equal. Okay, so that means 6 times 125, that gives you 750, and that will be 750 micro coulombs, I think. Yeah. And then if you want to find the energy E1, so that is in capacitor 1, and E2, we just use the equation that we just looked at, and we can find it. Okay, it will be in terms of millijoules. Right, now we get to the inductor. Okay, now inductor is like think about it, you get a coil of wire and it's wound around a former core. You get steel or iron or even air. You bring a coil of wire and you round it like this. Here is the symbol. The symbol looks kind of like coil, so you could understand how it's used. So current creates a magnetic field. Now that makes sense, because if you have iron and a coil is rounded around it, okay, that means there should be magnetic field. If you remember learning that before in school, that connects, doesn't it? And so therefore energy is stored by the virtue of that field. It's kind of like, think about it, a small electromagnetic device. Think about it like that. And so if you want to find the voltage through the inductor, we do L times the change in current over time. L is the inductance, okay? So, and energy stored is similar to the capacitor, like half times the inductance times current squared. So instead of V squared here, we have current squared. And the units are Henry, obviously again named after some dude who found out about inductors. So it's Henry, and it's usually, again, just like capacitors, very low number, millihenry, microhenry, and it follows Lenz's law. So if you know what Lenz's law is, where the induced voltage from the inductor always opposes the change that caused it. Okay, we will dive deeper into actually electromagnetic effect and things like that later on. So I think after AC circuits, I'll talk about electromagnets. Now, inductors. Okay, so if we have now inductor in series, it works just like resistors. So think about it. Inductors work like resistors in circuit. Capacitors are the opposite. Inductors here, in series, you get LT equals L1 plus L2 plus infinity. And then parallel is 1 over LT equals LT's total inductance. 1 over L1 plus 1 over L2 and blah, blah, blah. Now, we go next, right? Combining 3 inductors, okay? This is a worked example, okay? We have 0.015 Henry, 3 millihenries, and 9 millihenries. Now we should find the total inductance. Number 1, what if they were all in series? Number 2, what if they were all in parallel? And if you use equations, you will get the answers here. This slide is just for you to try to solve a question like that for yourself. Now, constant versus current, changing current. So if this is another example, worked example, if the current is constant, then we know change in current over change in time obviously is 0. Therefore, the voltage through an inductor is 0. Okay, you got these 2 inductors in series here, 0.5 Henry and 2 Henrys. Now we can find the energy for the first inductor using, again, the formula we saw before for the energy in an inductor, and then E2 again for the energy of the inductor. Now, let's say the current is interrupted and falls from 4 amps to 0 in 10 milliseconds. What we do, we know that 4, the change in current is 4 because it goes from 4 to 0, and then the change in time is 10 milliseconds. So that's 10 times 10 to the minus 3. You divide these two, you get your rate, okay, your rate of change of current. Now, if you want to find V, right, V equals the inductance times the change, the rate, the inductance, okay. So we will first find for V1, okay, that's the first inductor, 0.5 times 4 over 0.01, you get 200 volts. V2, you get 800 volts. Then the total voltage, you get 1000 volts, okay. Now, charging capacitors through a resistor. Here is where we start with the transient circuits, okay? Here is where you charge the capacitor through a resistor, or we're going to talk about inductors with resistors in the same circuit, which is very cool, actually, very interesting. So far, okay, every current and voltage has been constant, but what about now? What will happen now? It's going to change everything. Now we look at circuits where they can change with time. So we are going to start with the RC circuit. Now, RC circuit is resistor with capacitor circuit. As you see here in the picture, we got the VS, that is a voltage through the source, VS source. Okay, and what we do is we always, using Kirchhoff's law, voltage through the resistor plus voltage through the capacitor. That is because it's in series. Again, remember, series makes everything easier, but in real life, no, nothing is in series. All right, and then we know how to find VR. That is the current times the resistor in the resistance. And then VC we find using 1 over the capacitance times the integration, okay, of current times change in time. That all depends if, right, if there is change in time. So if time or change in current, if these two don't change, then now we differentiate and solve, right? We use something called differential equation. That's all mathematics. We end up with di over dt equals minus I over RC, okay? And that way we get to this equation. I, okay, the current, okay, in any time equals the current, initial current, multiplied by E is the exponential value, to the power of minus t, okay, so the negative of the time taken, okay, to get to that current, divided by the resistance times the capacitance. RC, we call it something specific. RC is called the time period, okay? So now, how do you find the initial current before it starts, or in the moment that it starts? We could say when the switch is closed. Also, when the switch is closed, that means we turn on the circuit, okay? It's the supply voltage divided by the total resistance, or the resistor here, to simplify it, okay? Now, here is the graph, okay? Again, remember we talked about RC being the time constant. The time constant, the Greek letter for it, it is tau. So it measures how quickly the circuit responds, because it's resistance times capacitance. So it depends only on the resistor and the capacitance, not on the supply voltage at all, okay? No matter how much you increase the voltage, it don't matter. It's the resistance and the capacitance. After one time constant, the current has fallen to I0 over E. So that is 37%. Now here we have two graphs, one for current against time, the other one is for voltage against time. So how the current changes against time, you get the equation. We have talked about the equation. Then for voltage against time in a capacitor, it is Vs times 1 minus e to the power of minus t over RC, okay? These equations, you could either remember them or they are probably coming up in your exams with it as well. Now, okay, so now this is a worked example. So we have a capacitor that is 10 microfarads in series with a resistor that is 0.6 mega ohms, okay, which is connected to a 100-volt DC supply. So it's very important to say DC because AC changes everything, okay? Just a reminder, I'm making a video on AC circuits after this. We will go very in detail with it. Now, so capacitor, okay, is already initially uncharged, so zero charge inside it. First of all, we need to find the time constant. To find the time constant, because we know it equals RC, we multiply the R and C, we end up with 6 seconds. Initial current. To find the initial current, we use Ohm's law. So that is supply voltage over the resistance. We get 167 microamps. So now, how much time do we need to reach to 80 volts? So we will put in the numbers into the formulas we learned. We'll get 80 equals 100 times sorry, 1 minus e to the minus t over 6, 6 is our time constant, we will end up with 9.66 seconds. So therefore, the VC and the current after 6 seconds, we again substitute the numbers into the formulas we learn, we end up with 61.4 microamps. So here, what happens is the current falls from 167 microamps to 61.4 microamps in by the time that the voltage reaches 80 volts. Okay, right. How do we, so in RC circuit, the current drops, okay, the current drops throughout time, but in an RL circuit, RL is where you have the inductor and resistor, the current actually grows, so it's the opposite. Okay, now we have a similar circuit, except we removed the capacitor and we put in the inductor. Okay, so again we use Kirchhoff's law. The supply voltage should equal VR plus VL, and so using Ohm's law, Vs over R minus I should equal L over R multiplied by change in current over time. Then we integrate and we end up with the formula that we are going to use most of the time. I equals initial I multiplied by 1 minus e to the power of minus RT over L. Okay, now the time constant tau for this circuit is L over R. Okay, so the inductor's equivalent of RC is L over R, the time constant. And usually after 1 tau, current reaches 63% of its final value. Okay, right, so to find the voltage in the inductor, we get the supply times e to the power of minus RT over L. Now, we have graphs here for RL circuits as well, the current versus time and inductance versus time, voltage versus time. It is the same as RC, except they are switched, okay? Because both of them do the opposite thing. RC drops the current and RL increases the current, okay? So they're mirror images of the RC circuit, these ones. Right, and you've got the formulas again shown. Now, this is a summary of everything we have learned. We've learned about resistance, we've learned about capacitance and inductance the most. So these are the equation, the universal pattern is like a format, right? If we are taking RC circuit, okay, and we know that voltage increases, then we are going to do the rising quantity, voltage increases, so it becomes Vt, okay, equals V final multiplied by 1 minus e to the power of blah blah blah, and current decreases, we use the falling quantity, and therefore LC circuit is opposite. And RC circuit, the current when it comes to the time constant, at the time constant, it falls to 37% of the initial current, and the voltage rises to 63% of the time constant, and the opposite for current voltage. Yeah. No, inductor. Oh my goodness. Anyways, guys, I'm so tired. It's been 30 minutes talking about transient circuits. But yeah, I hope you enjoyed the video and you understood how these work. I hope it was helpful for you. Next video I'm making it about AC circuits. That is reactance, impedance, and phasors. Scary words, I know, but hopefully I'll try my best to make it easier for you. There will also be concepts of complex numbers, so imaginary numbers I, or in engineering it's J. It will be very helpful if you already learned this, or you could learn it before learning about AC circuits. So I really think you should do that. But yeah, that's all. I hope you enjoyed the video and have a very lovely time.